The 2002 National Electrical Code Handbook contained a formal interpretation numbered 480-17 that addressed the requirements for concrete encased electrodes. This formal interpretation clarified specific aspects of the code concerning when a concrete encased electrode was mandatory versus when it could be omitted or substituted with another approved grounding electrode. Concrete encased electrodes, often referred to as U for grounds, consist of at least 20 feet or 6.0 meters of bare copper conductor, no smaller than 4 American wire gauge, encased within concrete. This electrode is typically located near the bottom of a concrete foundation or footing that is in direct contact with the earth. The purpose of a concrete encased electrode is to provide a low impedance path to earth, facilitating the dissipation of fault current and helping to stabilize voltage during electrical disturbances. The National Electrical Code, or NEC, outlines the requirements for grounding and bonding electrical systems to ensure safety and minimize the risk of electrical shock or fire hazards. Grounding electrodes play a crucial role in this process by providing a connection to the earth, allowing fault currents to flow back to the source and trip over current protection devices, such as circuit breakers or fuses. Without an effective grounding system, fault currents could persist, creating dangerous voltage potentials and increasing the risk of electrical shock. The formal interpretation number 480-17 in the 2002 NEC handbook specifically addressed scenarios where the concrete encased electrode might not be strictly required, offering clarifications based on the specific circumstances and other available grounding electrode options. It is essential to consult the actual language of the formal interpretation within the 2002 NEC handbook to fully understand the context and specific details of the ruling. The NEC undergoes revisions and updates every 3 years to incorporate new technologies, address emerging safety concerns, and clarify existing requirements. Therefore, interpretations and requirements can change over time. The fact that this formal interpretation was removed from the 2005 NEC handbook indicates that the code-making panel may have revised the relevant sections of the code, incorporated the interpretation into the main text, or determined that the interpretation was no longer necessary or applicable. When working with electrical systems, it is always crucial to refer to the latest edition of the NEC and any applicable local amendments or regulations. Relying on outdated information can lead to code violations and potentially compromise safety. The NEC provides detailed requirements for the selection, installation, and sizing of grounding electrodes, including concrete encased electrodes, rod electrodes, pipe electrodes, and plate electrodes. The choice of grounding electrode depends on various factors, such as soil conditions, available space, and local code requirements. Grounding electrode conductors, which connect the grounding electrode to the electrical system, must also be properly sized and installed to ensure effective grounding. The NEC specifies the minimum size requirements for grounding electrode conductors based on the size of the service entrance conductors. Proper bonding of metallic components such as enclosures, raceways, and equipment frames is also essential to create a low impedance path for fault currents and minimize the risk of electrical shock. Bonding jumpers are used to connect these metallic components together into the grounding system. The NEC provides detailed requirements for bonding methods and materials. Understanding the principles of grounding and bonding is crucial for anyone involved in electrical work, including electricians, engineers, and inspectors. Proper grounding and bonding practices help to ensure the safety of people and property by minimizing the risk of electrical shock, fire hazards, and equipment damage. The NEC is a comprehensive document that covers a wide range of electrical topics, including wiring methods, overcurrent protection, equipment installation, and special occupancies. It is essential to have a thorough understanding of the NEC to perform electrical work safely and effectively. The NEC is not a design manual, but it provides the minimum requirements for electrical installations. It is the responsibility of qualified electrical professionals to design and install electrical systems that meet the specific needs of the application while also complying with the NEC and other applicable codes and standards. Continuing education and training are essential for electrical professionals to stay up to date with the latest changes in the NEC and to maintain their skills and knowledge. The electrical industry is constantly evolving, with new technologies and materials being introduced regularly. It is important to stay informed about these developments to provide the best possible service to clients and to ensure the safety of electrical installations. The NEC is a living document that is constantly being revised and updated to reflect the latest advances in electrical technology and to address emerging safety concerns. The code-making process involves input from a wide range of stakeholders, including electrical contractors, engineers, manufacturers, inspectors, and consumers. The goal of the code-making process is to create a set of rules that are both safe and practical to implement. The NEC is adopted by state and local jurisdictions, which may also add their own amendments or regulations. It is important to be aware of the specific electrical codes and regulations that apply in your area. The NEC is an essential tool for ensuring the safety of electrical installations. By following the requirements of the NEC, electrical professionals can help to protect people and property from the hazards of electricity. Grounding is the process of connecting electrical equipment and systems to the earth. This provides a low impedance path for fault currents, allowing them to flow back to the source and trip over current protection devices. Grounding also helps to stabilize voltage and reduce the risk of electrical shock. Bonding is the process of connecting metallic components of an electrical system together. This creates a low impedance path for fault currents and minimizes the risk of electrical shock. Bonding jumpers are used to connect metallic components together into the grounding system. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. When an overcurrent occurs, the protection device will trip, interrupting the flow of current and preventing damage to the equipment or wiring. Wiring methods refer to the types of cables and raceways that are used to install electrical wiring. The NEC specifies the allowable wiring methods for different applications. Equipment installation covers the requirements for installing electrical equipment such as panel boards, transformers, and motors. Special occupancies refer to locations that have unique electrical requirements such as hospitals, hazardous locations, and swimming pools. The NEC provides specific requirements for these occupancies. Electrical safety is a critical concern for anyone working with or around electricity. It is important to follow safe work practices and to use appropriate personal protective equipment. Electrical shock can cause serious injury or death. It is important to avoid contact with energized electrical circuits. Electrical fires can be caused by overloaded circuits, faulty wiring, or damaged equipment. It is important to have a working smoke detector and to know how to use a fire extinguisher. Electrical codes and standards are constantly evolving to reflect the latest advances in technology and to address emerging safety concerns. It is important to stay up to date with the latest changes in the codes and standards. The 2002 NEC handbook, with its formal interpretation number 480.17, served as an important reference for understanding the specific requirements for concrete encased electrodes at that time. While the formal interpretation itself may no longer be directly applicable due to subsequent code revisions, the underlying principles of grounding and bonding remain essential for ensuring electrical safety. Understanding the historical context of code interpretations can provide valuable insight into the evolution of electrical safety practices. Consulting with qualified electrical professionals and referring to the latest edition of the NEC are crucial steps in ensuring that electrical installations comply with current safety standards. The formal interpretation likely provided specific clarifications on scenarios where alternative grounding electrodes could be used in lieu of a concrete encased electrode, potentially based on factors such as soil resistivity, building structure, or the presence of other effective grounding means. The removal of the formal interpretation from the 2005 NEC suggests that the code-making panel addressed the issues raised in the interpretation through revisions to the main text of the code, possibly incorporating the clarifications directly into the relevant sections on grounding electrodes. The NEC aims to provide clear and unambiguous requirements for electrical installations, and formal interpretations serve as a mechanism for clarifying ambiguities or addressing specific questions that arise in the application of the code. The code-making process is a continuous cycle of review, revision, and interpretation, ensuring that the NEC remains relevant and effective in promoting electrical safety. The NEC is not intended to be a substitute for sound engineering judgment, and qualified electrical professionals should always exercise their expertise in designing and installing electrical systems. Grounding and bonding are fundamental concepts in electrical safety, and a thorough understanding of these principles is essential for all electrical workers. The NEC provides detailed requirements for grounding and bonding, covering topics such as grounding electrode systems, grounding electrode conductors, equipment grounding conductors, and bonding jumpers. Proper grounding and bonding practices help to minimize the risk of electrical shock, fire, and equipment damage. The 2002 NEC and its formal interpretations represent a snapshot in time of the evolving landscape of electrical codes and standards. While specific interpretations may become outdated, the underlying principles of electrical safety remain constant. Continuing education and training are essential for electrical professionals to stay abreast of the latest changes in the NEC and to maintain their competence in the field. The NEC is a valuable resource for anyone involved in electrical work, providing a comprehensive set of rules and guidelines for safe electrical installations. However, it is important to remember that the NEC is not a substitute for sound engineering judgment and practical experience. Qualified electrical professionals should always use their expertise to ensure that electrical systems are designed and installed in a safe and reliable manner. Furthermore, local amendments may take precedence. The importance of consulting with local authorities having jurisdiction, abbreviated AHJ, cannot be overstated. Only by understanding the specific local requirements and following the NEC as amended can the safety and reliability of the electrical installation be assured. Soil conditions and other environmental factors can influence the effectiveness of different types of grounding electrodes. Therefore, it is important to consider these factors when selecting and installing grounding electrodes. The NEC provides guidance on how to assess soil resistivity and other environmental factors that may affect grounding performance. Regular inspection and maintenance of grounding systems are essential to ensure their continued effectiveness. Grounding connections can corrode or become loose over time, reducing their ability to provide a low impedance path for fault currents. Therefore, it is important to periodically inspect and test grounding systems to identify and correct any problems. Electrical testing instruments, such as ground resistance testers, can be used to measure the resistance of the grounding system and to verify that it is within acceptable limits. The results of these tests should be documented and used to track the performance of the grounding system over time. Electrical safety is a shared responsibility, and everyone has a role to play in preventing electrical accidents. By following safe work practices, using appropriate personal protective equipment, and staying informed about the latest electrical codes and standards, we can all help to create a safer environment for ourselves and others. The formal interpretation number 480.17 within the 2002 NEC handbook provided a valuable clarification regarding concrete encased electrodes, and its historical context contributes to a deeper understanding of the evolution of electrical safety practices. Always consult with qualified electrical professionals and adhere to the latest edition of the NEC and any applicable local amendments to ensure safe and compliant electrical installations.